it's a bit of an ugly way to work with it as well. So now I also can do like, because I know A is going to be a map, I can take blah blah out of that. No.
You need to define
yeah, okay, then. I'm not going to explain this syntax, but it's going to be something like this.
So in short, it's best to just define it with a struct.
Yeah, always better.
Okay, one of the shortcuts we do is this, that
So it's
if
going
you
to
have
be something like this. So now I'm going to say A is of like an empty interface, but this syntax actually says like, okay, A is
cause it a bit type.
So now I'm going to say B is A, but it's actually, I know that actually this type's inside of it. And then it's actually going to evaluate that at runtime. So if I say, no, I actually expect it to be A and a map of from string to int, and I compile this, compiling is fine, but at runtime it's going to say like, hey, A is not a map of string to int, no, it's a map of string to interface instead. But if I do this, and it's not even going to work. No, okay. The JSON package always creates a map from string to interface, unless I have an array here, for example. Now, if I still do what we just now was correct, and I do this, then it's going to say like, hey, wait a minute. A is not of type map string to interface. No, A is of type array of interface. So now, because the JSON was an array object, the JSON package is going to make an array. But you can do this to make it more complex. I can actually assign it in two things, and then if okay, then I'm gonna print this. Else I'm gonna print so I can actually, a second variable that I assign, I can a boolean that indicates if this cast was successful. So this is going to print, hey, wait a minute. So if you want to use this type of interface and unmarshal into that, if you really don't know what kind of JSON you're expecting and you do this, then you have to do a lot of things like, oh, I try to make this out of it, and then else, if that doesn't work, then okay, I'm going to try to make, maybe it's an array of interfaces. So then you basically have to typecast everything and see if your cast was successful or not. So I usually don't work with that kind of code. We usually use like really defined structures. And yeah, I would say this empty interface stuff, it gets used once in a while, but try to avoid it as much as you can. Ranges, okay. It's maybe also useful to know. If I have an array of integers, I can do for I0, I is less than the length of the
Spelling missing.
I can of course write this, what you would write
Equals to 0. I equals.
You can write something like this, which you would write in many languages, like just loop over all the things. In Go, you can also write for I, is the range in A. So now this is going to be exactly the same. So now I is every index in A, in A, because A is an array. I can also do I dot V. And V here, so now it's going to be I
Underscore.
Now I have to use that underscore thing again, so you can also do index, comma, value. So this is again going to be the same. If I have a map, for example, map from string to integer, I do four. And I can also do like for each key in a run now it's going to be 2 and 4, and K is something, so this is going to be K, and this is going to be KA, and the same again with key value instead. So basically range is just a simple way of writing loops over specific things. Now we get to the fun stuff, Go routines.
Yay!
This is why Go is a good server-side language. I'm gonna write a small example. Yeah, what's a good example?
TikTok.
So if I call function foo, that's gonna wait 2 seconds and then print foo, and then wait 2 seconds, print bar. Now what if at the same time of this I want to do other stuff? What if I have a function bar some other thing, and I want to execute bar as well? I'm gonna run this. Now it's of course it's gonna execute this function, wait 2 seconds, execute bar, and then execute this function. But if they can actually run at the same time, because bar doesn't depend on anything from foo and it doesn't matter, I can use the go keyword. And the go keyword, I think most people are probably familiar maybe with threads or processes. The go keyword executes this method, but starts it in like a different thread, you can say. It's not really threads, but it's basically the same as threads. So if I run this now, it's gonna print blah blah immediately, because
You need to sleep. Yep. Yeah, concurrent stuff is fun.
anyway, it's gonna go execute foo, so it's gonna print foo, but it's also gonna execute bar immediately, because this foo, it's not gonna wait for foo, it's gonna put foo on a different thread and continue executing bar. So that's why it's gonna print blah blah first actually. It might also print foo first, it just it's just random, because it just depends on which thread gets the CPU first. And then it's gonna print bar later. This time.sleep that I have to do is a bit tricky. If I don't do that, we're not gonna see anything from foo, because foo will actually get started in a different thread, but the main function is gonna end right away, and then it's gonna not wait for foo to continue. Just if the main function ends, your program ends. So that's why I have to make sure the main function actually waits longer than the foo function takes.
So, but does foo continue to run, or
No, if I do it like this, then really my program just stops after the main returns.
so then
So if you're lucky, foo might get like a little bit CPU time before your program exits, but it's not guaranteed at all.
so then in like real programs, if your main one finishes,
Okay,
then you
in
are
real programs you would do something like you would use the sync package, and then you do
Mutex. Add one with group.
you can do a wait group. I do pass it to foo, and then
Wait.
I'm gonna wait here, and in foo, oh wait, before I start foo, I'm gonna say
Add one.
I want to wait for one thing. Foo is also gonna have a single wait group as argument, and then you
Then
say
you're done. Defer normally.
done. So now I've got a built-in thing which is called a wait group. I say it needs to wait for one thing, then when I call wait, it's gonna just pause that thread, just keep hanging on this function until done is called at least one time. So now I don't need this sleep. I'm gonna say run. So it's
Add one. Yep.
So So now it's gonna work.
Oops.
Got it.
Why?
I forgot. Done. The weight group done. Weight group done is decreased, right? You might need to double check.
Should be the other way.
Okay, I'm not sure
Do you need
why
that
it's
remove
so
book?
weird. Okay, now
I don't have my
know exactly
docs
why.
for me.
But at least you can see that it does this after everything is done. Yeah, I think you're right.
Normally use channels for this. I do my laptop,
Yeah, no,
so
I
I
have
can
to make a pointer out of that. I think you're right. I have to pause. Actually, you are right.
Ah,
So,
okay.
okay,
Oops.
what I did just now is pass it by value. So now I make here a wait group that needs to wait on one time calling done, but I pass it by value. So actually this wait group is a copy of this wait group. So when I call done here, this one will be done, but not this one. So I actually need to pass a pointer to that wait group. So now this WG is pointer to this one, so when I call this done, it will actually be this one that is done, and here wait will continue. So that works. I can do exactly the same with this one, if I don't know which one's faster or whatever. And will be exactly the same. But now they both go into a go routine, and oh, sorry, I have to wait on 2 now, otherwise it still doesn't work. And here is something where if you have a construct like this, it's very useful to have the defer keyword, because I might have full returning from multiple locations in my function, and I always need to call done, because if I don't call done, then it's always gonna say like deadlock. Because if I don't call that done, then this wait is gonna wait for something, but the go is actually smart and sees like, hey, but nothing is executing anymore. This function was done, this function was done. I'm waiting for nothing, so that's a deadlock, that's a mistake in your program. So if I want to make 100% sure I always call done, I just start my function with defer wait group with done. So now I'm 100% sure whatever code I write here, if it panics, if it returns in multiple places or whatever, done will always be called. So running this,
Fatal error.
no, it's gonna be fine.
Okay, so can we call, okay, so when you write server application, you actually form multiple threads,
Yeah.
multiple worker. Can you do that with Go routine?
Yes.
Huh?
The short answer is yes. If you use the normal this one, most of all the different incoming requests will be running in the different Go routine.
Okay, okay, okay.
So if you use an
Automatically,
HTTP package, Go has a very simple built-in HTTP server which looks something like this, like you start a server on port 8080, you have a function that handles your request. Each time you receive a request, the HTTP package will like start this function in a different Go routine.
Okay, so let's say we do another network application based on
Yeah.
HTTP. So let's say we also have multi-threaded. The answer is yes, you already answered me. Because any network application requires you to form multiple workers to make things
Yeah.
faster.
Yeah, so this will automatically start multiple
But
workers
this for
already.
HTTP, but not others.
Yeah, it's the same.
Well,
it's the
it's
same.
a lot
For
of
every
most
single
things
connection,
like Yeah.
like I don't know, Telnet for
Most
instance,
packages use
yeah,
Go routines for stuff.
you use if you actually define let's say a Telnet handler, either you write it yourself. Every time an incoming request comes in, after you actually accept that, you'll be running the that particular connections all the code there inside a Go routine. So you don't need to make sure that you re-release and actually check back who else is actually
Yeah, so
trying to
usually
connect.
if you have something like
Yeah.
most of the time you just when you have work to do you start it in a Go routine, and actually a Go routine is not a separate thread, so it's not like you're starting a lot of threads. Go will start a number of threads. Most of the time it will start as many threads as you have cores in your system, and then it will smartly schedule all these Go routines on those threads. And so in Go, when you do a blocking call or something, like, well, this is blocking, obviously, it waits for 2 seconds, then that will not block anything else except for this specific, you do it on a separate Go routine. Go routines are really cheap. I think it's like a 4 KB per Go routine or something. The stuff we have, because we serve a lot of ads, we have thousands of requests incoming per second on single Go processes. We have like sometimes like tens, sometimes, no, I would say tens of thousands of Go routines, separate Go routines running at the same time. And Go does that with like barely any CPU usage. So it can, if you make 100 threads in your operating system, that's probably going to be a bit slower. But Go routines are really light, so thousands of Go routines, no problem at all. Now, what if foo had a return value? Because we started in a different Go routine, I cannot do something like this. I cannot assign the return value of foo. So if it has a return value, the Go keyword is sort of useless, well, not useless, but you have to do it differently. So let me show that as well. For that, we can do 2 things. We can do this. So for example, if I want to return an integer, I can do an integer pointer. Integer. This. Wait until it's done. And this is going to do. So now we're going to wait.
Nope.
Let's make 1 second. So now wait for 1 again. So now I have a pointer to an integer, and in the Go routine I can assign a pointer. So I have the integer itself here. I just pass a pointer to that integer, and here it will have assigned 2 to that.
Okay.
But this is a bit dangerous, because if I would do this,
Yeah.
and I would do what's the
Can you put
Plus
it
1
right
or
there?
I can
something.
do this.
Then the plus 1 is matter.
Y is also an integer. I'm going to assign Y.
Still technically work most of the time. It will work most of the time.
So now I'm going to start 6 Go routines, each
At
one with
6.
a different value for Y, and it's going to, at the end, it's going to, let's remove this part, so it's going to print a lot.
Your weight group need to add 6.
Yes, I need to wait for 6 things to finish. So now it's going to assign the return integer as Y. What is this going to print? I don't know. 2. Okay, this one is always going to print 2 because the Go playground is made to be deterministic, so everything always executes in exactly the same way. If you would run this in like a real environment, you would have no idea what it's going to return.
Do not implement a dice like that.
It's
Yes.
even unsafe, it can even crash your program. If I say this is a slice of integers,
Ouch.
Okay. Possibly a bad idea.
It is a bad idea. It's not possibly a bad idea.
in the playground I have no idea what this is actually going to do. But let's find out. Oh wait.
Just remove that.
No, I have to do that. Okay, it's actually not crashing. but in theory this could crash because a slice, of course, in the Go runtime itself, a slice is implemented as some different memory positions, like it has a length, it has a capacity, it has a place in memory, it has all kinds of properties. So if you do this, then one Go routine might be increasing the size while another is trying to write to it, and you get all kinds of stuff mixed up, which could definitely cause errors. How we can fix this, the Python way would be this.
It's a global lock.
I could just,
Python?
is everyone familiar with mutexes or locks? It's basically, if you have l.lock, then only one Go routine, only one thread can pass through, and then until that one Go routine or thread unlocks it, then one of the others. So this means that basically this line of code can only be executed by one Go routine at the same time. So now it's actually safe. And I did capital L. Still some weird order because we still have no idea which Go routine gets the CPU at which time, but now it's safe.
Is that exclusive lock?
Yeah.
Yes.
We can also do read-write
Mutex means mutually exclusive,
Yeah.
so it's exclusive.
You can also do a read-write, and then you can do air lock, which means you acquire a read lock, and if you have a read lock, you're only supposed to read. So this is a write operation, so that's not. So a read-write lock, if you have readers and writers, a write lock is exclusive. So a write lock only one thread, one Go routine can get. A read lock, a lot of threads can get at the same time, but not the same time as a write lock. So if you have a lot of readers doing something and only once in a while you write something, then a read-write mutex is better because all those readers can go do stuff at the same time. We can even, if we want, we can pass it. There's an argument if you want. You don't want the global lock.
Does the variable being capital or non-capital makes a difference? Like the
Capital-
functions?
Yeah, but we get to that later.
Yep.
Okay, so can you pass queues?
Public versus non-public.
Queues between processes?
Yes, I'll get
Okay.
to that now. So this is one way to do return values. A nicer way to do return values is what is called a channel. So if I know I want to return an integer, for example, I can make a channel of integers. Let's call it x. And we had y still as integer. And now I can say a channel, you can put stuff in. So this is the syntax to put stuff in. So I have a channel x of it's a channel which has integers in it. So you can see a channel is sort of an array, only like array already protected by mutex. So I'm putting y into the channel. Now I'm actually gonna do.
The channel fixed size or?
By default, it's single size. It's just one. You can only have one value in the channel.
So I make
By default.
I make the channel, so a channel of integers, and here I can specify the size if I want.
Yep.
Right now I know I'm going to
Six,
put
yep.
6 things in, so let's make it a buffered channel with 6 things.
Looks like really a queue.
It's a queue.
Yeah, it's a queue. So that's channels I actually don't, because channel is a built-in thing. I don't have to take a pointer to the channel. Don't ask me why, but and now I can do here. I can do. Let's make x again. X is an array of integers, and now I can say x is x, and I take something out of the channel, and I can do this 6 times.
Oh, we cannot pass it into library class yet.
Sorry?
We can't pass the queue the channel into library.
No, you cannot cast the channel. You really have to take them out one by one. So if I run this, so 24.
Okay, X.
So now it's gonna do the same. So what we have now, we start all these go routines. One by one, they're gonna put their value into the channel. And here I'm going to take stuff out of the channel 6 times, put it, append it to my array, print the array. If I say I'm gonna take 7 things out, then it's gonna be a deadlock again. So now I'm waiting for a 7th element in my channel, but there's no other go routine putting anything in my channel, or there's no other go routine executing at all. So it's a problem in my program again. What's actually better is if you do something like this. Oh no, that's actually also gonna break. Never mind. So this takes stuff out. Channels are always already protected by mutex, so you don't have to write a mutex around your take and get operations with channels.
Can you use LAN channel? Can you use LAN channel? Something like that.
You could, but it's not really a good idea to find the length of channel. Always return the size of the buffer, isn't it?
What? Sorry?
If you take a len, len,
Oh, the length of a channel.
Returns the
That's
size
how
of
many
the buffer.
elements are in there. So
Should
if I, for example, I can wait here first.
and
Before this, I can. Let's press both of them. The length of the channel and the capacity of the channel. Now we wait until everything is done, and we print it again. So now, because at first there's nothing in my channel, so the length is 0, but I made a buffer channel with 6 possible entries, so the capacity is 6. After all the go routines are done, putting their stuff in, the length is gonna be 6, because there are 6 items inside, and the capacity is gonna be still 6. So I can do here, could write this in theory. This will work. Of course, if I move this weight here, then it's not gonna work, because now we have no idea how much stuff is in there already, so that would still work. I think the capacity here. Another interesting thing, if I wait here first, so now all go routines need to be done before I start taking stuff out. If I now make my channel too small and I run it, it's gonna be a deadlock again. So now 4 go routines got to put their value into the channel, but the 5th and the 6th go routine, there's no space for them. No one is taking the values out yet, because that's still waiting. So those 4th and 5th go routine, they cannot finish, they cannot put their stuff in, so they're blocking on putting stuff in. So they're never calling done here. So basically Go, and so this one never gets done, so Go detects this and says like, oh, there's another bug in your program. You're trying stuff that doesn't work because deadlock.
So if you have a dynamic amount, how do you
Well,
handle that?
usually if I do 0 here, so I don't make it buffered at all,
range.
I will put this behind this. So if I do it like this, that's gonna work fine.
normally we just use
why is
range.
this not working fine? Maybe.
Yep.
I think I actually.
You're waiting
No.
for
F6.
no.
Cap, oh sorry, the
Yeah.
capacity is of course 0 now, so I'm gonna take 6 entries out. So this is gonna work. So what's going to happen now is all these go routines start, they're going to try to put stuff in the channel, but they're only gonna put stuff in the channel if this one is reading it. Well, that's starting immediately, but if I do like this, that's still gonna work. But now all those go routines I remove this time no sleep, it's still gonna work. So now all these go routines are starting, we don't sleep anymore, so they're immediately gonna try to put their value into the channel, but no one is reading from the channel yet, that's sleeping. But sleeping is still fine, it's not a deadlock yet, you still have stuff going on. And after the sleep is done, we're gonna read this from the channel. And because we read all of them from it, like one by one, we're gonna read each go routine's value, and each go routine is gonna put their value in here, be done. So in the end, they're still all done. Hope that's a bit clear. It gets a bit more complex right now. Yeah, let's keep channels at that.
You could just range over the good, yeah.
No, you cannot. Okay, and you can also write this, so I can have a
You have to close
value.
it though.
So I can range over the channel, so a range over channel just keeps taking stuff out. But this is not gonna work, it's gonna cause a deadlock again.
You need to
Because this
close the
range
channel.
only stops when you close the channel, so
Go routine. Wait group. You could actually use the wait group to actually check whether it's actually done. Then you close it.
close, so you can actually close the
Yep.
channel, and if you close it, then no one can write to it anymore. If you write to a closed channel, that's an error, panic. If you do a range on like a closed the channel, then it stops, the for range stops when the channel is closed. So now I have another go routine that's going to close the channel after 2 seconds, so this is gonna be fine. Because after 1 second, it's gonna try to read everything. So at some point, this range C is gonna be blocking because there are no more new values being put into the channel. But then after 2 seconds, it's gonna be closed, so this range is gonna stop, and then it's all fine. So what we could also do indeed is do this. Instead of waiting here, we could do this.
Yep.
So now we start a bunch of go routines. We wait until all of them are done, and when all of them are done, we close our channel. And here we're just gonna read from the channel for as long as we can. So this is still gonna work without a deadlock, exactly the same.
One thing you guys may want to realize is that because of the way we actually use this one, so long as the for loop there, it's just that it's waiting for the channel to be finished and
Yeah.
closed. So if you guys want to easily implement, for instance, timeout, you just need to have another go channel, sleep for whatever your timeout is. If you close that channel, your program will quit. So that means is that if you're spawning about 6 threads, and if they're doing some heavy processing, let's say even getting results from over the network, and you really don't want to wait for 10 seconds, 20 seconds, 1 hour, there's a timeout of whatever seconds you want to specify.
so
If you
here-
close it, you're done.
Here I could do time dot sleep time dot second times 2, or let's make it 3. Here I'm gonna say time dot sleep times duration of y. So now each go routine is gonna sleep for a different duration. Like this go routine is gonna sleep 1 second, this one is gonna sleep 2 seconds, 3 seconds, etc., etc.
Why can't you just why comes directly?
Sorry?
Why do you use standard duration?
Because Go, everything is really strictly typed. One example I didn't give before, if I have x is an integer with 64 bits, it's just gonna stop. And this Go routine that's supposed to put 4 in is going to sleep 4 seconds. So that doesn't get the chance to put it stuff in the channel because our main already exited, so our program already exited. So this is like sort of a way, like you have a bunch of workers, they all do stuff, like this might be some CPU heavy computing or some I/O or whatever, and we're going to have a timeout of 3 seconds, and after 3 seconds we just want to take whatever we have and nothing more. Okay, that's channels. Well, panic I already covered a little bit. Let's go to cover for a little bit. If I have a function, I can have another function, and in this function, something goes wrong, some will panic. Okay, this one calls bar. Okay, so what this is gonna do is obviously it's gonna call and then it's gonna print something. Okay, it's obviously not gonna get here because it calls blah blah panics, so it's gonna print and it's gonna print a stack trace. Same happens if I do I have to do this, of course, because if I don't do this, then it's already going to complain at compile time, like I have C here, but I'm not doing anything with C, so I do this. So now I'm at this, and now I have a division by 0 here. This is also the same as panic, so this is basically the same as
Panic.
well, yeah, well, runtime, error, whatever.
Whee.
Whatever. That's basically comes down. So panics and runtime errors like exceptions like that are the same. Sometimes we want to be able to handle this. Sometimes we might depend on a library that has a bug like this in it, or we have some user input that we don't really check which can cause this, or might be reasons. What we can do, let's move this one here. So this is still not going to execute this. What we can do is we defer a function. One interesting thing you can see is this.
Yep, note, okay, pump.
So actually, defer also gets executed when there's a panic. So when you have a panic or a runtime error or something, it's still going to unwind the call stack and it's still going to call all the defers. What we can do in a defer is we can use the recover function, which is a built-in function. And what the recover function will do is, if there's nothing going on, it return nil. But if there's an error going on, if we're unwinding because of an error, it will assign that error to, well, it returns that error, and then it will stop being an error. So if we do actually do this, okay, I cannot do that.
No, it goes through.
I can just do this. So if I do this, now it's still going to execute this blah. Because here, this caused an error, but we're going to unwind the stack, so we're going to roll back, we're going to execute this defer, which does a recover, and it recovers from the panic. We can even assign it to something, and we can do like this. So now this print line is going to be executed first. It's going to print like, oh, I have this error, but after that it's still going to continue. So here also, oh no, this actually not. This is not going to be executed because bar caused the error, because this function is immediately going to return because of that error in bar, and it's going to execute that defer. So with recover, we can basically recover from panics, and we can make sure that if you really want to have like super safe code, then and you want foo to never crash your program, then you always like defer and recover. Now if we don't have an error happening, it's just gonna print here nil. So usually it will look something like this. Or do something else with the error probably. So now it only does this if there's really an error. Another interesting thing is if we have foo, which returns, for example, an error and an integer, and it returns integer and an error. normally if we were to and no error, what we can actually do, we can name these variables. So we can say this is, for example,